We begin by showing a 1 hour satellite movie from yesterday afternoon, when you might have noticed between 3 and 4 o'clock these rib-like structures in the clouds that were really quite dramatic as they came across in the late afternoon sky. And these are wave clouds, and you can see them developing on the very large scale across much of the southern state part of the state here in the satellite image yesterday. And you might say to yourself, boy, this looks a lot like the kind of ripples that get left in sand or something at the beach as the tide goes out or comes in. And it's exactly the same process. These little ripples in the clouds are local regions where the air is forced to rise, and they're adjacent to, in the little spots in between, spots where the air is forced to sink. And the air that's rising and sinking is very close to saturation in these cases. And so when it bumps up in a turbulent updraft, it produces a cloud. And when it bumps back down, it sinks away. The cloud dissipates quite rapidly, so you get this rib-like structure. So if you were flying through this in an aircraft, you'd be bouncing up and down because these really are evidence of little bumps in the flow. And those bumps in the flow are a function sometimes of turbulence that can be produced by dynamics, or it could also just be daytime heating in certain other instances. I think probably yesterday was probably a turbulence feature, somehow tied to what we'll talk about some weeks from now, that is the jet stream. So a really, really interesting set of wave clouds yesterday that you may have noticed, and you're getting a view of them here from the satellite perspective. So it's pretty exciting stuff to have seen this so vividly yesterday. Also, I want to point out before we talk about the current weather, yesterday afternoon, or Monday afternoon, I guess was after our lecture, it was really windy all day Monday, and you might, of course, want to know how that's related to what we've been talking about in class. And recall, we've been thinking about how the horizontal pressure gradient force is really the only one of the three forces we've investigated thus far, the horizontal pressure gradient force, Coriolis force, and friction, that can actually initiate the wind. It's the only one that can make things move that might originally not be moving. Everything else just modifies the movement. And the pressure gradient force can be described graphically by looking at a map where you draw sea level isobars. There's a lot on this chart, but the only things that matter really are the black lines. Those are the sea level isobars at about noontime on Monday. And you can see that the horizontal spacing between successive isobars, all drawn at the same interval, so each one is as small as the one before it in terms of the increment, is really intense across the upper Midwest. So it's really tight spacing of these black lines, and that is indication of a very strong horizontal pressure gradient force, which translated on Monday afternoon into very strong, persistently strong winds. If we had been down over Tennessee and parts of North Carolina, where you can see there's almost no pressure gradient force, as evidenced by wide spacing between the black lines, you would have had a perfectly calm day down there. But not so near us, and that was a function of a really intense cyclone that at the time was getting itself organized and continuing to develop over southern Lake Winnipeg in Manitoba, Canada. And so we're beginning to talk about development, how there's convergence at the ground into a cyclone because of friction, and then there must be divergence at upper levels. We'll be talking about that a little bit today in the lecture. Okay, so this is an example of the intensity of the horizontal pressure difference across our region, which resulted in extreme winds on Monday. It was quite a windy day. Here's our surface map today. That cyclone that was over Lake Winnipeg is now moved off to the east of Hudson Bay, and it's just about off of our map. Trailing to its south is a cold front along which there's considerable precipitation all the way from, the Gulf of St. Lawrence down to northern Louisiana. We'll talk about that in a minute. In the wake of this cyclone, because these cyclones and anticyclones come in succession, they're a wave-type phenomena. We'll begin talking about that. And here you can even see evidence of that. Here's an anticyclone off the Atlantic coast. Here's the cyclone we've been talking about. Here's the next anticyclone in the sequence, which has begun to invade over us. And so the winds will slacken as the day goes on. In fact, they've already calmed to nothing. Accompanying anticyclones in the late winter, early spring, though, is very often chillier air. And so you notice that it's considerably cooler over our portion of the country today. In fact, the whole western two-thirds of the United States this morning is dominated by this giant anticyclone. And the temperatures have responded. As you can see, across much of the country, they're pretty chilly. 7 and 9 degrees in parts of North Dakota, 10 degrees in International Falls at 8 a.m. It was only 29 at Madison, so we haven't been below freezing in a couple of days. And then a very sharp contrast of temperature, sort of at the leading edge of that anticyclone, where it's 51 in Little Rock, but 72 in New Orleans, 48 in Nashville, but 65 in Atlanta, 70 in Jacksonville. So a very sharp horizontal temperature contrast at the front edge of this invading anticyclone, and that's actually along the cold front of the cyclone up in Ontario. And so we'll talk about those structures a little bit more. You might guess, based on limited experience that we've had together, that this sizable temperature contrast may also be accompanied by a sizable dew point contrast. And boy, is that true. Look at this dew point contrast across the southern states this morning. 27 is the dew point at Little Rock. 70 is the dew point in New Orleans. So you could drive through this thing and break out into a sweat. It's that intense of a gradient of dew point. And that, of course, testifies to substantially more water vapor in the air over the southern states along the Gulf Coast as compared to even Little Rock or St. Louis, where the dew points are in the 20s. And it's even lower here at 16. So bone dry, chilly Arctic air. And at the boundary between this very much colder, and in this case, much drier Arctic air heading into this moist air, you might expect there's going to be some interesting weather. And sure enough, we'll see that in just a second. So first, let's take a look at the satellite image over the continental United States, or movie over the continental U.S. and adjacent waters. The only substantially organized cloud feature across the continental 48 is this cloudiness that is dangling south of the intense circulation associated with the cyclone that was closer to us on Monday and now is well to the northeast of Hudson Bay. So this is kind of impressive convective activity blowing up here. We'll see on the radar in a minute. Notice these clouds just grow quickly from zero to really cold cloud tops over Mississippi, parts of Louisiana, and Arkansas. And that's going to be some pretty heavy weather down there. We'll see in just a minute. But that's all along the cold front, which is on the eastern edge of the invading anticyclone. The radar that goes along with it depicts some of the details of that precipitation and the cloudiness. So in Pennsylvania, New York State, you get probably local spots where there might be some intense downpour, but it's even worse down in Mississippi and Alabama. You can see the leading edges of red that are pretty intense. I would not be surprised to see some more severe weather down over these two states and parts of northwest Georgia during the morning today. So we may see some hail reports or some even tornadic activity again in this already ravaged southeastern part of our country. But that's really the only precipitation of interest across the country, and this is really kind of scary down here again. In fact, it's prompted the Storm Prediction Center to put a slight risk for severe weather across, central North Carolina all the way down to the southern part of Mississippi, and we're seeing some of that area already light up. So this is looking like a pretty decent forecast. Marginal risk for such weather just to its north as well as to its south, as you can see, and we're in the free and clear. We'll see more of these as the semester goes on because the weather will get perhaps more interesting during that time. Okay, I want to show you one more current observation map, and that is the 500 millibar map from last night. Unfortunately, I don't get the 12 o'clock London time map in time for class, but this is last night, and you can see the structure that I'll now call again a broad trough in the flow. The black lines are the equivalent of isobars at 500 millibars, which is about 3 miles or so above the ground. And so where those black lines are tightly spaced together, there's really strong winds. Where they're less tightly spaced together, such as on the western shore of Hudson Bay, they have really light winds. So at Churchill, Manitoba, 15 knots is a very light wind at 3 miles above the ground. Whereas at Green Bay, where there's a tight spacing, we had a 95-knot wind this last night. So substantially different winds. I'll zoom in a little bit, and you can see how, again, conforming with the geostrophic wind, which we've talked about in class, that is a balance between the pressure gradient force and the Coriolis force. When you don't have friction, which you don't have over the Great Lakes at 3 miles above the ground, the winds are going to be really close to that geostrophic balance. And sure enough, just about everywhere on this map, the wind bob is parallel locally to the geopotential height lines, or the isobars, the black lines that are on this map. So you can see a really isobar parallel flow everywhere across North America. Just about every single station really shows that. If you get into the high mountains in northeast Nevada, maybe there's a little bit of an angle of the wind across the isobar, but not very many places demonstrate that at this level in the atmosphere. So this geostrophic wind we've talked about is a really good approximation to the actual winds, and you can see that vividly illustrated day after day. In the next few lectures, we're going to be talking about what is it about these broad upper troughs and their cousins, which in this case, with the isobars pointing poleward in a bulge, a ridge. So here's a ridge off the west coast, and here's a trough over the central U.S. Here's another ridge off the Atlantic coast of Canada, and then another trough off of the Atlantic coast. and they come in different sizes, but you can kind of see the characteristics of them. How are they related to weather systems is what we're going to really be looking at as we move forward. Okay, so there's another example of today's 500 millibar map. And finally, the West Coast satellite image, a rather placid situation across much of the western coast of North America, with the exception perhaps of British Columbia and then into southern Alaska. But the continental U.S. coast is really clear today. Very, very nice. There's an organized weather system north of Hawaii that's kind of trying to get its act together. There's one at about the date line that's spewing clouds in a clockwise fashion, sort of an anticyclonic fashion, just at the end of the Aleutian chain. And then there's this major cyclone that's invading central and northern British Columbia into the Yukon Territory. But that's it. It's a fairly benign weather map, satellite movie for the Pacific Basin. We've seen them a lot more active earlier in the semester, and we may well see that later as well.